Welcome to Physics 102A Homework Solutions. This is Chapter 8, Rotational Motion. We start with number 20. A disk with radius 1.5 meters, rotational inertia of 34 kilograms meters squared, has a 160 Newton force applied tangentially to its rim. If the disk starts from rest, the angular velocity at the end of 2 seconds is what? All right, let's get a picture, see what we're looking at. There's the disk. The force is applied tangentially. That means it is perpendicular to the radius. I've written out all the given information. It says it starts at rest. Omega naught is 0. What is the final omega? And t is 2 seconds. We need to find the acceleration first. And so using that torque is moment of inertia times alpha. Torque is force times lever arm. Now there is also a sine theta component in there, but because it's being applied tangentially, that theta is a 90-degree angle. So the sine of 90 is 1, and it just becomes force times the lever arm equals I alpha. We'll solve for alpha. So it's force times the lever arm, that's the torque in the numerator, divided by moment of inertia in the denominator, and we get an acceleration of 7.05 radians per second squared. Now we can apply that to a kinematic equation. Since we're given omega naught and t, now we know alpha. We can solve for omega is omega naught plus alpha t, and we get 14.1 radians per second. Numbers 21 and 22 go together. 21 says a 46-gram golf ball has radius 2.13 centimeters. Assuming uniform density, what is the ball's rotational inertia? All right, uniform density, that means it's a solid sphere. We look up in the table in the chapter and it says moment of inertia for a solid sphere is 2/5 mass times its radius squared. There's the maths, there's the radius. We're going to need that in MKS units to get kilograms meters squared. So 46 grams is 46 times 10 to the 3, or times 10 to the negative 3 kilograms. Then we have 2.13 centimeters. We can say that's 2.13 times 10 to the negative 2 meters. Be sure to square it, and we get a moment of inertia of 8.3. You can see down below here, it's 8.347896. But to give the answer to number 21 with two significant figures, that's 8.3 times 10 to the negative 6 kilograms meters squared. Number 22 says, what is the rotational kinetic energy of the golf ball in problem number 21 when it's rotating at 80 hertz? That's 80. Now, hertz, remember, is cycles per second. It's not radians per second. So kinetic energy is moment of inertia times omega squared. We're going to need omega. So 80 hertz, the rotational frequency or the angular frequency, omega, is 2 pi times that. So we get 502.6548 radians per second. Kinetic energy is I omega squared. Now be careful, don't take a rounded off answer, even though I answered number 21 as 8.3 times 10 to the negative 6. We don't ever want to plug a rounded off answer into another equation. So we'll use the full digits, or at least take it out 6 or 7 digits that the calculator gave me. Plug it in, we get 2.1 joules. Number 35. A lawnmower blade accelerates at 98 radians per second squared starting from rest. What is its angular velocity after 2.5 seconds? Answer in radians per second and RPM, which is revolutions per minute. Well, we're given alpha. It's at rest, so omega naught is 0. Time of 2.5 seconds. What is its angular velocity? So we'll use omega equals omega naught plus alpha times t. And we get 245 radians per second. Converting that to revolutions per minute, you can see we want to turn radians, or first let's turn the per second into per minute. So 60 seconds over a minute, the seconds will divide out. And then let's turn the radians into revolutions. So that's 1 revolution is equal to 2 pi radians. The radians will cancel out, and we're left with 2400 RPM. Number 36, a diver jumps from a 10-meter high tower and hopes to complete 3.5 somersaults. What should be his rotation rate? Now the problem isn't clear what it means by rotation rate. There are 3 ways that we can express the rate of rotation. We can express it as how many turns per second, or somersaults per second, I'll just call them turns, and that would be the frequency F. We can express it as radians per second, that would be omega, or we could express it as how much time it takes for each somersault, that would be seconds per turn. That's the reciprocal of frequency F. So I'll just answer it all 3 ways. So we know that he wants to do 3.5 somersaults. What we don't yet know is how much time he has. So he's jumping from a 10-meter high tower. So jumping from 10 meters, let's use kinematics of linear motion. So y equals y naught, which is 0, v naught t, which is 0, equals 1/2 at squared. So the time to fall a certain distance is given by this equation. Time equals square root of 2y over acceleration. And we'll plug in the values, falling 10 meters, accelerating at 9.8 meters per second squared. For the person to hit the water, he has 1.429 seconds. Okay, now let's answer the rate of rotation 3 different ways. We can answer it as frequency, how many somersaults per second, 3.5 turns per 1.429 seconds, and we get 2.45 turns per second. We can answer that as how many seconds per turn, just take the reciprocal of frequency. So 0.408 seconds per somersault. Or we could answer it in MKS units, radians per second. Let's take F, the frequency, multiply by 2 pi, and we get 15.4 radians per second. Number 39, a dentist drill accelerates from rest at 615 radians per second squared for 2.1 seconds, and then runs at constant angular velocity for 7.5 seconds. Through how many total revolutions has the drill turned? All of the kinematic equations that we use rely on constant acceleration. So if we have a situation like this where there are 2 separate accelerations, we have to divide it up into 2 separate phases. So let's divide it up into what I'll call phase A, when the drill is speeding up, and then phase B, when it's going at a constant speed. And what we're going to do is find how many revolutions it turns through in each of those phases. So for phase A, it's starting at rest, omega naught is 0. There's alpha, 615 radians per second squared. Time, I'll call it T sub A, is 2.10 seconds. What is omega 1? And I'll solve that in a bit. Phase B, whatever omega 1 was, so whatever the angular velocity was at the end of phase A, that's what it is throughout phase B. It's constant. And phase B lasts for 7.5 seconds. So we still don't know what that omega 1 is, but we'll get to it. The total angle that the drill spins through is the angle from phase A plus the angle from phase B. So let's do phase A first. We can say that theta sub A is omega naught times the time of A, but omega naught is 0, so I've just crossed that out, that's 0, plus 1/2 alpha times T sub A squared. And so we'll plug in those values for phase A, and we get 1356.075 radians. For phase B, we're going to need to know what the angular velocity is at the end of phase A. So we'll use this equation. Omega 1 is omega naught, which was 0, plus alpha times the time of A. So by the end of phase A, it has sped up to 1291.5 radians per second. Okay, Now, we're going to use that information as we assess phase B. The total angle turn for phase B is its speed, so omega 1 times the time of B. And there is this acceleration component of that kinematic equation, but there is no acceleration, so we're just left with that the angle is omega 1 times time of B. So we have 1291.5 radians per second times 7.5 seconds, and we get the total angle turn is 9686.25 radians per second. So we have theta for phase A, theta for phase B. Let's add them together. We get 11,042.3 radians. What did the question ask? Through how many total revolutions has the drill turned? So we'll divide by 2 pi to get the number of revolutions. So we get 1760 revolutions. Number 41. A centrifuge rotating initially at 9,000 RPM slows to 5,000 RPM with constant angular acceleration over 3.5 seconds. What is its angular acceleration? Through how many revolutions does it turn while decelerating? And through what distance does a point on the edge of the centrifuge at radius of 9.4 centimeters turn during this time? All right, let's take the given information. We have omega naught and omega 1 in RPM. I've converted those to radians per second. We're going to need that to get through this problem. And you can look back at problem number 35 where I did the conversion from radians per second to RPM. But there's the values in radians per second. A is asking what is the angular acceleration. So we'll do the change in omega over time, omega 1 minus omega naught. It's negative because it's slowing down. We get negative 120 radians per second squared. Question B, through how many revolutions does it turn while decelerating? We use this kinematic equation, omega naught t plus 1/2 alpha t squared. Remember, when you're doing alpha, don't do the rounded off answer of negative 120, but use it with more precision. So I've used negative 119.6797 radians per second squared, and we get 2565.65 radians. Convert that to revolutions, so divide by 2 pi, and you get 408 revolutions. Or you can see in the green ink here, you could also use this kinematic equation. Omega squared equals omega naught squared plus 2 alpha delta theta. Solve it for delta theta, and you'll get the same answer. Question C is asking about a distance that a point on the edge goes, that it travels. And let's look at this picture here. If we have an angle and the radius of the circle, we're looking at the arc length, which is S. And S equals r theta. As long as theta is in radians, this equation works. S equals r theta. So 9.4 centimeters times 2565.65 radians, which is what we got in part B. And we get 24,117 centimeters. Such a large number. Let's scale it down a bit. So 241 meters. Number 54. Using astronomical data from Appendix E, compute Earth's rotational inertia, assuming the planet is a uniform solid ball. All right. Well, uniform solid sphere, moment of inertia is 2 fifths mr squared. We need the mass. We can look that up. You don't actually need the Appendix E table. You can use the back of the book. Now, one little thing that's different, mass is 5.97 times 10 to the 24th kilograms, and the radius, I've used here 6.38 times 10 to the 6th meters. In the back of the book, it says 6.37 times 10 to the 6th. I used a different source for that, but so given the numbers that I used, we multiply that 2 fifths mr squared, we get 9.72 times 10 to the 37 kilograms meters squared. Number 55, use your answer to the preceding problem to find Earth's rotational kinetic energy. All right, kinetic energy is 1/2 I omega squared, and we got I for number 54, but we need omega. So how many radians per second does it take for Earth to spin around? Well, it'll spin around once, that's 2 pi radians, and it does it in 24 hours. That's 86,400 seconds. And so when you do 2 pi radians over 86,400 seconds, that's going to be the radians per second. Then we plug it into this equation with I, and we get a kinetic energy of 2.57 times 10 to the 29th joules. Number 57. The circular blade of a power saw has kinetic energy 44 joules. Its rotation rate drops to half. What is the new kinetic energy? I've solved this two different ways. You can see my blue ink and my green ink. Let's look at the way I've done it for blue ink first. We write out the given information, kinetic energy sub 0, because we know kinetic energy is changing, so we're going to use the 0 and the 1 subscript, so 44 joules. We know that omega 1 is half of omega naught, and we want to solve for kinetic energy 1. So one solution is to start with kinetic energy 1 is 1/2 I times omega 1 squared. Then we're going to substitute in for omega 1, it's 1/2 omega naught, so we have this here, 1/2 omega naught squared. And that 1/2 squared becomes a quarter, and I'm going to take that quarter and slip it out to the side. So here we have 1/4 times 1/2 of I omega naught squared. Well, 1/2 I omega naught squared is the original kinetic energy. So we can say that it's 1/4 of the original kinetic energy. So that's what I've written out here. And 1/4 of 44 joules is 11 joules. Let me show you another technique for solving this problem, and you can decide which one you like better. We can set up a ratio. Sometimes when you have quantities that are changing, a useful thing to do to see how another quantity changes is set up a ratio. So we are given the original kinetic energy. We want to find the final kinetic energy. Set them up as a ratio, K1 over K0. And in the numerator, we'll do K1, so that's 1/2 I omega 1 squared. In the denominator, we'll do the original K0, 1/2 I omega naught squared. And look what happens when we have this ratio. The 1/2s divide out. The moments of inertia divide out. And we're left with this simple ratio of omega 1 over omega naught squared. So then in the next line, I'm going to take omega 1, and you can see up at the top of my screen, that's 1/2 of omega naught. So I'm going to substitute for omega 1 in this numerator. I'm going to call that 1/2 of omega naught. And so here we have this line. Now notice the omega naught divides out, so we're left with 1/2 squared. And so we're left with this nice simple relationship that the ratio of K1 over K0 is 1/4. So then we can say K1 is 1/4 of K0, and we get 11 joules. Number 75. An auto mechanic applies a 65 Newton force near the end of a 35 centimeter long wrench. What is the maximum torque? We're going to use this equation that torque equals force times lever arm times sine theta. The mechanic is applying the force near the end of the 35 centimeter long wrench, so we'll take 35 centimeters as being the lever arm. The maximum torque, well, the torque is going to depend on the angle over which it's applied. Maximum is going to be where sine of theta is 1, and that's going to be with an angle of 90 degrees. So the force applied is going to be perpendicular to the lever arm. So we have 65 newtons times 0.35 meters times that 1, or sine of 90 degrees, and we get a torque of 23 Newton meters. Number 79, Two children with masses 35 kilograms and 40 kilograms sit at opposite ends of a 3.4 meter long seesaw with mass 25 kilograms, with the fulcrum at its midpoint. With the seesaw horizontal, find the net torque on the seesaw and its angular acceleration. And on this page, I've done part A, the net torque. Let's draw a picture here. We have the seesaw. We have the child, I'll call him 1, and the other child 2. And the one on the left is applying a torque, or applying a force rather, of his mass times g. So that's going to be his weight going straight down. You notice I've drawn right angles there. That's the significance of the seesaw being horizontal, so that all of their weights are applied at a perpendicular angle. And this child is at a distance, we'll call it R1, of 1.7 meters from the fulcrum, so that is the lever arm. Child 2 is 1.7 meters in the other direction, with weight of m2 times g. And then there's also the torque. It's going to come out to be 0, but the torque of the weight of the seesaw itself. Now, that is m, I've called it m sub s, mass of the seesaw times g. But since it is at the center of mass of just the seesaw, it's on the fulcrum, and that has a lever arm of 0, so it's not going to count for anything for torque. It's important to note the directions. Notice that each of the two children is pushing a torque in opposite directions. So call one of them positive, the other negative. It really doesn't matter which one you call positive and negative, but they have to be opposites of each other. I'm using the convention that clockwise is a negative angle. So the child on the right is pushing in a clockwise direction. And counterclockwise is a positive direction. So the child on the left is pushing with a positive torque. And also we're going to need to remember that torque is force times lever arm times sine of theta. But to make life easier for us, sine theta is equal to 1 in each of these cases because they're perpendicular. All right, let's set it up. The sum of all the torques, the net torque is, we take the positive, which is torque 1, plus torque of the seesaw, and then the negative, so minus torque 2, because it's in that negative direction. Then we plug in the values, force times lever arm, so m1g r1, plus mass of the seesaw g times lever arm of 0, minus m2g r2. And so now we put in the values, 35 kilograms times 9.8 newtons per kilogram times 1.7 meters. The seesaw doesn't add any torque, but I've left that 0 in there. Then minus 40 kilograms times 9.8 times 1.7 meters. You can see in this line, I found the torque, the contribution of each part of this system. So the child on the left is giving a counterclockwise torque of 583.1 newtons per meter. The seesaw itself is 0. The child on the right is contributing 666.4 newton meters in the clockwise direction, and that's why it's negative. So in the end, it comes to be negative 83.3 newton meters, or if we give it as a magnitude and direction, we can say 83.3 newton meters clockwise. Now problem 79 continues with part B. Find the angular acceleration. So now that we know the torque, we need to find acceleration, and I'll do that on the next page. All right, this was our result from the previous page that the torque is 83.3 newton meters clockwise. To find acceleration, if you go to the bottom here, the middle of the page, the relationship is torque is moment of inertia times alpha, which means alpha is torque over moment of inertia. So we need to find the moment of inertia. You can look at the picture down below to remind yourself of the setup, but the moment of inertia is going to be the contributions of child number 1, child number 2, and the seesaw. So let's take them one by one. Child number one. Child number one is a mass that's a certain distance from the pivot. So that's m1r1 squared. And we plug those values in, we get 101.15 kilograms meters squared. Child number two, same thing, a mass that's a certain distance from the pivot. m2r2 squared, plug those in, we get 115.6 kilograms meters squared. We also have to account for the seesaw itself. Now the seesaw can be taken as approximately as a rod that's being rotated about its center. And you can look that up in chapter 8. There's a table in chapter 8, a rod rotated about its center. The moment of inertia is 1/12 ml squared. So 1/12 of 25 kilograms times its a length of 3.4 meters. We're going to square it, and we get 24.083 kilograms meters squared. This gives us a total moment of inertia when we add all those up of 240.83 kilograms meters squared. And now we plug that into the equation that alpha is torque over moment of inertia. And we take the torque that we got, divided by moment of inertia, and we get 0.346 radians per second squared. And because the overall torque was in the clockwise direction, the acceleration will be in the clockwise direction. Number 80. A meter stick is initially balanced on a fulcrum at its midpoint. You have 4 identical masses. 3 of them are placed atop the meter stick at the following locations: 25 centimeters, 45 centimeters, and 95 centimeters. Where should the 4th mass be placed in order to balance the meter stick? All right, very important that we draw a picture here. Let's draw it. We have we have 3 masses that have been placed. It says the meter stick is balanced on the fulcrum at the midpoint, so at the 50 centimeter mark. I've drawn here the first mass at 25 centimeters, 45 centimeters, and 95 centimeters. We're going to be figuring out the torque, the total torque here. So for torque, remember, we're going to need the lever arm of every one of those weights. And so when we apply it, I'll show you on the next page, but we're not going to use these meter stick markings. Those are just the positions. We need the lever arm. We need the distance from the fulcrum. And if the fulcrum's at the 50 centimeter point, then this first one at 25 centimeters is going to be 25 centimeters away from the middle. So I've made R1 be 25 centimeters. The one that's positioned at the 45 centimeter mark, that's 5 centimeters away from the middle. And the one that is at the 95 centimeter mark, that's 45 centimeters away. So I've written up here at the very top what the different lever arms are. All right, so we're going to place a 4th identical mass. We need to think about what side we're going to put it on. Is it going to be on the left or the right? Now, one thing we can do is just make a guess. We can just guess left or right and go with that. But another way we can figure it out by finding where is the current center of mass. So if we take the center of mass of those 3 masses, the position times mass, remember, so 25 centimeters times m plus 45 centimeters times m plus 95 centimeters times m divided by 3m, we find that the current center of mass of those 3 masses is at 55, meaning it's right where my marker is. So if we want to add a 4th mass and we want their total center of mass to be over the fulcrum, we're going to need something that's more to the left. So the 4th mass will need to go somewhere on the left. All right. So now let's go to the next page. The 4th mass will need to go on the left. And so let's set it up that way, that the net torque is going to be 0. So we have the torque from 1, and it's positive because it's pulling down, it's pushing down in the positive direction or the counterclockwise direction, plus the torque from 2, plus the torque from 4. Now I've made that a plus because I'm assuming, as I found on the last page, that it's going to need to go to the left. So it's going to be somewhere with those other, with R1 and R, or with the one that I've called number 1, the one that I've called number 2. It's going to be on the left, so a positive torque. Now the third one is on the right. It's pushing in the negative direction, so we'll say minus torque 3, and they all need to come out to be 0. Now remember that force is lever arm times weight times sine of the angle, but all those angles are 90 degrees, so it's just going to be the weight times the lever arm. So here we go. From torque 1, we have mgr1. From 2, it's mgr2. From the mystery mass, mgr4. And then for the third one, minus mgr3. You can factor out mg, so we have mg times r1 plus r2 plus r4 minus r3 equals 0. Here we have a situation where we have 3 factors multiplied that equals 0, and one of them has to be equal to 0. So either the mass is 0, which it's not, or g is 0, which it's not, or the thing in parentheses is 0. And so the only possible choice is the thing in parentheses being equal to 0, so we set it equal to 0. R1 plus R2 plus R4 minus R3 equals 0. And we want to know what R4 is. So we solve that for R4. We get R3 minus R1 minus R2. Plug in those values. Again, we're using the R values, the lever arms, not their positions on the meter stick. So it's the numbers I've written up there in the green. So 45 centimeters minus 25 minus 5, and we get 15 centimeters. Now, what that means is that that's the lever arm of the fourth mass. The fourth mass must be 15 centimeters. We've already established that it's on the left, and we established that mathematically by saying plus torque 4. So to the left of the midpoint, which is at 50 centimeters. So if it's 15 centimeters to the left of the midpoint, then it's got to be placed at the 35 centimeter mark, right where my marker is at the top of the screen. Now, by the way, on the previous page, I said we could guess whether it goes on the right or the left. And that guess would have panned out by, let's say I guessed it would be on the left, then that would be plus torque 4. What if I had guessed incorrectly that it was supposed to be on the right? Well, then I would have said, okay, it's going to be somewhere over here, pushing in the negative direction, and I would have made this, right where my marker is, that plus sign would have been a negative sign, a minus sign. Okay, so guessing that it's on the right, I would have made this a minus sign, and what we would have found, if you work through all that math, we would have gotten R4 would be negative 15 centimeters. And so we would have to interpret it this way, that assuming, making the assumption that that fourth mass is on the right, we would get that it's a lever arm of negative 15. That would tell us that we guessed wrong. It's 15 centimeters away from the pivot, but on the other side, 15 centimeters to the left. Number 81. A meter stick of negligible mass has a 0.20 kilogram mass at its 35 centimeter mark and a 0.4 kilogram mass at the 75 centimeter mark. Where should the fulcrum be so the meter stick is balanced? All right. Let's look at this picture here. We have our two masses. We don't know where the fulcrum is supposed to be. In the previous problem, it was right in the middle at the 50 centimeter mark. Here, we have to find where is the balance. So we can use concepts of torques to figure this out. And let's draw the picture, and we're going to define R as the distance that the fulcrum is to the right of mass number 1. And if there's 40 centimeters between mass 1 and mass 2, and we know that because the one's at the 35, the other's at the 75, there's a 40 centimeter difference. What that means is that the fulcrum is 40 minus r away from the 75 centimeter. Those become the lever arms. So the one on the left has a lever arm of r. The one on the right has a lever arm of 40 minus r. All right, let's use the torque equation. So the sum of the torques has to be equal to 0. And we're going to solve for, again, we want to solve for where is r. What is r? That'll tell us where the fulcrum needs to be. So we have torque 1. I've made it positive because, as you can see in the picture, it's pushing. Its weight is pushing in the positive direction. Minus torque 2, because mass 2, its weight is pushing in the negative direction. So torque 1 minus torque 2 equals 0. Now, the torques are, we have m1 times r. I've left something off here. I forgot to write because I factored it out without even writing it, but it's actually m1g times r. And this one is m2g times 40 minus r. But I just, without even thinking about it, I just factored out g. So we have m1r minus m2 times 40 minus r equals 0. And let's solve for r. So m1r minus, we're going to distribute the m2. That's going to be 40m2 plus m2r equals 0. Solve it for r, so I'm going to collect the terms. These are two terms that have r in them. So m1r plus m2r. Let's collect them together as r times m1 plus m2. The other term, I'm going to add it. So this minus 40m2, add it to both sides, and we get 40m2. So in that, I've done about 2 lines of algebra. Make sure that you understand the different steps that I've gone through. We solve for r, and we get 40m2 over m1 plus m2. Plug in the values, and we get 26.6 repeating centimeters, or 26.7 centimeters. Now let's interpret what this means. We go back up to the picture. And okay, so this is how we defined r. The fulcrum must be 26.7 centimeters to the right of the 35 centimeter mark. And so 35 plus 26.6 repeating, and I'll round that to the 10th of a centimeter. We get that the fulcrum needs to be at the 61.7 centimeter mark. There's a much easier way. Now that we've gone through using torques, there's actually an easier way to solve number 81, and it involves center of mass. So the fulcrum needs to be at the balance between those two masses. It says the meter stick is of negligible mass, so we don't have to worry about the meter stick itself. Let's use center of mass equation. m1x1 plus m2x2 over m1 plus m2. And so we do the first mass times its position at the 35 centimeter mark, plus the second mass times its position at the 75 centimeter mark, divided by the sum of the masses, 0.6 kilograms, and we get that the center of mass is at 61.7 centimeters, and that's where we need to put the fulcrum. And that is the end of the Chapter 8 homework. Have a great day.